is moving relative to that one, that's the first velocity, and then there is not. And then both systems are trying to characterize how that object moves from their own reference frame. So I'm not going to go on the theoretical derivation, but the basic idea is that these end up as the velocity perceived by each of the systems depend on their own velocity. Okay? So to try to remember this type of problems that involve 1, 2, and 3 elements, I told you to use these mnemonics. If you use it, you have your own theory about that. So use that. But in this one, if you read it, there's a boat sailing with one speed, some direction, north of east, in the ocean. But the ocean itself, water, is flowing with another speed in some other direction. And they ask, what is the magnitude of the velocity, the speed of the boat relative to this hypothetical coast, or it could be a helicopter flowing on the case is that this other element is not on the water flowing with the water. So it could be the coast, or it could be a helicopter that's looking at this from the top, so that it's not moving. Okay. So the coast is essentially the idea that represents the thing that is not moving, right? The big chunk of rock, right? Earth. That is not going anywhere, and then the water is flowing, and the boat is on top of the water by swimming, right? It's rowing, it's trying to do its own thing. So the way I recommended doing this is to write the name of the 3 elements, the coast, then you can put here the sea, or the current, or the water, whatever you want to call it. And then the last element is typically the one thing that you want to study from the perspective of the 2 systems. And in this case, it's a boat. Plane or something like that. So both the person that is on the coast and both, I don't know, Neptune in the sea, whatever you want to call this, want to know how the boat is moving relative to their system. Okay. So these are the 3 elements. The way to figure out whether the velocity you have is this one, or this one is with this mnemonics or rule is you connect this last one with the first one, and then going down to do the same thing, passing through the intermediate one, and then you write the next. Okay. So it is a velocity addition for sure. You are adding 2 velocities to find a third. Which ones are you adding? That's what we're trying to figure out. So in this case, starting from the top, we're trying to figure out the velocity of the boat relative to the coast. And for that, we're going to need the velocity of the boat relative to the, let's say, sea, for example, boat relative to the sea. And then we have the sea relative to the coast. Okay. So notice that because this is an addition, it's commutative, so you could do this one first and then this one. It doesn't matter, right? The most important part, and that's why I have different colors, is that this one is the one that is on the other side of the equals, and the other ones you can just do one or the other. So then let's read the problem, right, to figure out what they are giving us and what they ask for. So they say, the boat is sailing with this speed, and then the ocean has a current. Okay? The idea of the ocean has a current means that it's independent of the boat. You can remove the boat, and the water is still there flowing. So from the coast, you can see the water flowing whether there's a boat or not. Okay? So that one is very clearly the sea current relative to the coast. So that one is the one that they say is 50 meters per second and direction is 23 degrees, let's say south of east. Then the other one is the boat itself. It's called like the person swimming in the river, right? You're rowing, or it's a motorboat, but it has a direction, or they have a compass and they're trying to go in this direction, and the engine is going or letting the boat go at 100 meters per second. So that is the velocity of the boat relative to the sea, because again, you can remove the coast, but maybe you don't see if you're in the ocean, right? So you're just guided by the cardinal points. You have your compass, you don't really need to see the coast, and then you're going at that velocity. You're doing that on the water for sure. You're swimming, but the water itself is moving you, so because you're swimming inside that medium. You're not in the coast, you are in the water. And this is the one that is 100 meters per second in the direction of 70 degrees. Okay. And the last one is the one that you're looking for. So there's no this that they don't give it to you, they ask what is the velocity of the boat relative to the coast. So this is what you're looking for. So long story short, you have 2 velocities, add them. Okay? Then unfortunately life is not that easy, it's not okay, so I add them, it's 100 plus 50 is 150. The problem is that these are vectors and they have directions. Okay? So you have to add them as vectors with components like the arrows that I just showed you a second ago. Right? So you have an arrow like this and an arrow like this. You add them but not one after the other. They have their own direction. Okay? So you need to break this into pieces like Newton's law, like anything that is a vector. So you have to find the x and y components of these velocities. requires triangles. Okay, they this problem they actually show you, so there's no question, right? There's like the cardinal point, these are the directions. If they don't, right, you can read it right. So the first one was 70, and it was north of east, so this is east and north, right? So it's north of east means from the east and towards the north, and the other one was south of east. So that means that we are going in this direction from the east towards the south. And it was a little bit more, so this one is 23 and the other one. And then you have the numbers, so you can just find the magnitude of the components. That is, this is the arrow that represents the full speed, the magnitude of this vector. We want the components. So this vector is going to be a combination of vector like this and another one like this, right? So that then you add. What are the components, right? Trigonometry. So this one is going to go with the cosine, and this one is the other way around. This one is going to go with the sine, and this one is going to go with the cosine. And then for the other one, we're going to the same. We're going to have an arrow to the right, and then another one that goes down. Okay. Notice that this one has to be negative because it's pointing down. So the problem tells you 23 degrees south of east. You can either write the angle like this, so 360 minus this, or write this as negative 23. Okay, the calculator doesn't care. Both things give you the same answer. Or you can do just 23, but then put the negative sign manually. Okay. So that is then the velocity of the boat relative to the, what did we say, sea or ocean? Velocity of boat relative to the sea. We'll have two components, right? X and Y, and same thing for the ocean. That is the velocity of the sea relative to the coast, the velocity of the sea relative to the coast, and you have X and Y components. So we have to find them. The boat is, I don't remember, 100 in a direction of 17, so it's 100 cos 17, 100 sine 17, and the boat, the current is 50 cos 23, 50 sine 23. Alright. Then with numbers, what that right, so it's 100, so it's going to be mostly in this direction and a little bit on the other one, and then for this one we can do the same thing, right? So once you have the components, then sketch the other one, right? The total velocity, which is right the formula that we were sketching here, right? The velocity that we're looking for is the addition of these two, but with their components. So the velocity of the boat relative to the coast, x, the velocity of the boat relative to the coast, y, are going to be the addition of these two. So in the x-axis, this is going to be x-axis, and then the xc, x, y, and then sc1. That is we're going to add this one here, and then the other component is cosine of 23 times 50 is 46, and the other one is cosine of them. So this one adds with this one. So this is going to be 97 plus 46. And this one is going to be 29 plus 19. So 97 plus 46 and then you have to square them and then write the magnitude of this. Let's see, it's going to be the square root of 143 squared plus 40 squared. And that's going to be the answer. Okay, so you just find the magnitude. The key of the problem is two, one, figure out whether you have to add them or subtract them, and the other one is then you do the square root and add them. 43. IP that a lot of intermediate steps, so you put all of this together in the calculator. It should give you. Oh yes, sorry about that. I keep saying it and then I miss it. Right? So this has to be negative, so this will go negative there. So this is a lot smaller. Sorry about that. And rounding or something like that, 143. So I forgot my own calculator, and then the other question here is what's the angle? I had to correct this morning, so there was a typo in the exam. For this one, once you have this, right, you can see that the magnitude of the velocity along the x-axis is now a lot larger. It's 143 and this one is 10 because of, as you were saying, one is negative, right? So there is the ball is going in this direction, the water is going in this other direction, so both of them are pushing the ball in that direction, so it goes a lot faster to the right, but one is going up and the other one is going down, so that it slows down, so it's going to go a lot faster to the right than it's going to go up, because there's slow, along the up direction it's going to slow down because of the current, so that goes down, gives you a vector that's going to be presumably more parallel to the x-axis, so if initially it was 17, we're expecting a number that's going to be smaller, this one should be of the order of the tangent of the y component over the x component, so that's 10 over 143, another 143, 10 over 143. Let's correct this about 4 degrees or 3.9 again. With the rounding, I probably like did a lot of intermediate calculations, so you give it all together in the memory and you just operate, and there's less rounding error, but that is basically the answer. Okay. And it makes sense, right? So you can double check with the idea of the velocity. You go a lot faster on the x-axis, not so much on the y-axis, so that brings down the angle. Right? You are now more aligned to the x-axis because it's an increase in that direction, and then you slow down on the y-axis. Alright, so that was problem number 1. There's another one about the
On our midterm, we had that question. They asked like, what would you have to do if like you wanted to like sail at like a direction that was like, what if like how would you solve a problem if they asked like, what if the person wanted to sail so that he was like 5 degrees south of east? Like how would you solve it then? Like what degree would you start at, and what's
so
like
the long story short, right? If you want to make this problem, generally forget about these specific numbers, right? You end up with some velocity that you want to know is some velocity that you know times constant that you know constant that you know, and that's the x component, that's the y component, and then these ones, again, this is the x component, the other one is the y component. Okay, so all of these numbers you know, and then you just plug them in. The key idea here, right? So this one is 17, 23, you get the velocities, you get numbers, so these turn into numbers, you add them, and then you put them together to get the magnitude of the velocity. And then the angle is the inverse tangent of this equation. So if you wanna set, right, so you know that this is happening, there's a current, and you wanna compensate for the current because you're going to that port or that other and it's in that direction, then you know in which direction you wanna go. So it's like you know this angle a priori, right? So in this type of problem, you're given all of these, and then you figure out these two things. If you know where you're gonna go, what you mean is that you know this number a priori, right? So you know you wanna go in that direction. So you have to fold in that into the equation. The way you fold that into the equation is that it has to be in that component. So we can call this now the final velocity. So that number there is the final velocity times the cosine of an angle that you know, because the problem is gonna tell you, wait, you wanna go in this direction, so how do you compensate? Okay, and then again, the other component, right? Then the final velocity times the sine of theta. Okay, and again this number. Okay. In that particular midterm, it was easy because what they were saying is, imagine that you want to go straight north. So a straight north means that this is 90, so the sine of 90 this becomes 0, so that equation becomes a 0. Okay. So then, because this is a 0, then you can just figure out what is this other angle that or you can figure out the velocity you want to go, right? So it makes it easier, but in a more generic problem, when they give you the direction that you want to go, what they're giving you is this other piece of information that goes into this equation. So now you can solve, because the right side of the equation you know, you have two unknowns, so they will give you one, you can solve the other, right? So one way could be square one and square the other, so that the addition of the two, right? So this one square is this, and this one square is that. You add them, and this one becomes one, and then you get this number, and this is basically squaring this one and squaring it. So I'm only sketching this because that is a complicated problem. I'm not going to ask you to do it generically. In that midterm, it was easy because you wanted to go straight north. So then one of these equations becomes 0, and then you don't have to do this complicated in square. Okay? The one equation, so for example, this one becomes exactly 0. Okay? So these two numbers have to compensate each other, or you can take this other equation and then you can solve for the angle. Okay? So, again, if you have more questions, you try to do it that one, the problem in the midterm, then ask me again, we can solve it numerically. I wanted to just touch on a few other ones briefly before we move. This one, I think the one that was referring to, this one is the soccer player that tries to score. I think we solved this one as an in-class problem specifically, so you probably have it like resolved in detail. So I'm gonna skip it, but it's a projectile motion problem just to give you the overview of the type of problems that you can have. This is relative velocity, that is projectile motion. This is a Newton's law problem, right? Going down the slope with or without friction. I remember, we can read it. And this one is an object rolling up. So it's like energy conservation. We did one like this the other day. I think exactly like this with the ball rolling and going up. So it has kinetic energy of translation, but also rotation. And then you trade kinetic energy for elevation, right? So it's a energy conservation problem. Okay. So let me touch on Newton's law one briefly if you want. Again, this is problem 2 in 2 parts. Again, there are 2 questions. I think we alluded to this, right? You have to figure out one thing and then the other, right? So they are connected because you're calculating parts of the same number, like in the velocity here, the velocity and the direction. And again, I'm gonna put the full PDF, so you can read the whole thing and you can ask me, email me, or I'll be here on Monday for the other exam. So in this here problem, we have a person going down this slope. Just going down this slope. So that's the way, that's the inclination. And this is a Newton's law problem, right? The way we draw this is that the person's weight is resting on the surface, but the surface is slanted, so it happens that the normal has to be perpendicular to that surface, and that typically takes us to this sort of reference frame where we're looking for the parallel and perpendicular direction, because when the person moves down with some acceleration, it's along that direction. So So that's in this case, they ask specifically for that. What's the acceleration first without friction, and then another one with friction. So again, there are two questions, but they're not connected. You can like solve them separate. They are different questions. So this one is going down. In these ones, again, the goal of this one is that you show me, right, that you know how to operate with these vectors. The key idea is that the weight needs to be broken down into pieces because it's not along the parallel or perpendicular direction. So it will have a component in this direction and another one in this direction with this angle that is the same as that other angle. Okay. So when you say you want to figure out the acceleration, you use Newton's law. The sum of all the forces gives you the acceleration, but it's a two-dimensional problem in a strange direction. So you're going to break this into two. The sum of the forces parallel give you the acceleration parallel, which is what we're looking for. But the sum of the forces in the other direction also gives you that acceleration. In this case, what we usually said in this problem is that we don't want the person on the skier to take off. We just want her to slide. So this is typically zero. The person is at rest in that direction, and this is the sliding down velocity. So we just need to figure out the components. In this case, because there's no friction, there's literally only normal reactive force and then the weight that has two components, the weight perpendicular and the weight parallel. So in the parallel forces, we only have the weight that traditionally is just mass times gravity, but that is in the vertical direction, right, in the x and y directions. So when you calculate the parallel and perpendicular components, you have to do it, right, in this case, the parallel goes with the sine. So it's mg sine theta, and the other one is mg cos. In this case, theta is 35 degrees. And the mass is 80 kilograms. You can do it. I'm not going to do it numerically, just to show you how to do this. Then, in this one, the answer is the sum of the forces along the parallel direction is just this one, because the normal is perpendicular, right? The normal only has perpendicular direction, and then this is the perpendicular component of the weight. So along the parallel direction, it's just the weight. It's just the weight that pushes you down the slope. So this is going to be mass gravity sine theta equals the mass of the object times the acceleration, and then you solve for that. Then let me remind you that this is not a formula that is on the equation sheet. So when you have an inclined plane, you cannot write down this because it is correct, but then you are getting it out of thin air. You don't know why that happened. You are postulating that that is true, and it is, but you don't know how to solve the problem. You are not showing me how to solve the Newton's law problem. Plus, if there is some other component or a rope or something that's happening, then this might not be true. So you have to solve it. Again, you don't have to give me all of this detail, but again, you have to indicate what are the forces and they go into which component of the Newton's law equation and how you get the acceleration. So in this case, the acceleration is just gravity times the sine of theta, but I need to see some of the work done to figure out that you know how to solve the problem, not that you get formulas for a slope and then you try the formula to see if this works in this particular problem. Then in the other direction, what we have is that because this has to be a zero, that means that the normal, that in this case, is pointing up in this direction, okay, and the component of the weight in this direction points down. They have opposite directions. We have the normal pointing up minus the weight pointing down have to be zero, or in other words, the normal has to be equal to that component of the weight. Also not true in all the situations, so again, it's not an equation. You have to solve Newton's law. So in this case, it is true, and the normal component will be mg cos theta. Okay. They didn't ask for it in this problem. In this problem, they want to know the acceleration, so it's g sine theta. But in the other question, they say now do the same thing, but there is kinetic friction. Okay. When you have kinetic friction, the object is going down, basically pushed by the perpendicular component of the parallel component of the weight, right, that goes in this direction. Now you have a friction in the parallel direction. The only thing is that, as we know, and it's on the equation sheet, the frictional force is proportional to the normal, so you do need the normal from the previous part of the problem to understand this. Okay? And they say this coefficient is just 0.3. So this changes the equation in the parallel direction because you do have the parallel component of the weight as before, but you also now have friction in the opposite direction. Is that a question?
What were you saying? cosine instead of sine if the n is perpendicular?
It's from this triangle, right? Because the triangle, remember, is flipped.
Oh, okay, yeah.
Right, so the inclined plane, this flips. If you look at the big triangle, it's like this, but this one is like that, right? So the angle is here instead of here. This is this one. This is this one. So the cosine ends up here, whereas this one is here, and this is the sine. This is the sine, right? So it's kind of like flips because the triangle is rotated. So then we write the parallel component as we did before, right? This was mg sine theta, and then we have to write the friction, that is the coefficient times mg cos theta, mg cos theta. And that gives us the acceleration. So as before, the masses simplify, and you end up with the acceleration is g sine theta minus mu g cos theta. This is not an equation. It's the result of a problem. You cannot memorize this. This is not an equation sheet, so don't memorize it, because if you just write this down, this doesn't show me that you know how to solve any kind of problem that involves forces in different directions. You just memorize a formula for acceleration in an inclined plane with friction. And in this problem, it happens to work. Okay? It's kind of like in the projectile motion, there is a formula for objects that go up and down. Okay? That only works, right? The time of flight or the range, that only works when the object starts and ends in the same elevation. So it is for a very specific setup. Okay? The goal with Newton's law is that you have a tool, which is force equals mass times acceleration, that allows you to solve any kind of problem with any kind of forces. Okay? In this one, then you arrive at this equation, then you can plug in the numbers and work out. Okay? So that you can solve that way. So very briefly, other than the ones that's shown in the graph, this one is the one about the bowling ball going up. So again, it's just an object going up this ramp, so it's a change in energy. Notice the moment of inertia is here because now the ball is an object that is resolved and it's spinning, so you need this number. So if it's a sphere, the moment of inertia is 2 feet. Mass radius squared, you need that to include the kinetic energy of rotation. Okay? And other than that, there was another problem about the satellite spinning around Mars, so it's a gravitational problem, Newton's law of gravitation. There's a merry-go-round here with a person located somewhere, so it's like the problem with the kid on the merry-go-round moving around, right? So moment of inertia of the disc, plus a kid somewhere, and you figure out how fast is the spinner or the moment of inertia of the system. This is a shopping cart colliding with another one, and they merge into one, so it's an inelastic collision, right? Relatively simple. The other one is the projectile motion for the soccer player, and this is the relative velocity. And this one has 10 questions. So this one doesn't have anything else. It's literally that, mostly these 4 problems, and then one about collisions and moment of inertia.
Are final have figures drawn like that?
It might. I haven't decided. Sometimes I put them next to the problem. Sometimes I put them at the beginning, just to help, right? Especially if like there is directions to clarify the directions of things. So it might. It depends on when I'm doing it, whether I know it in advance and I can put them all together, or sometimes I just put them inside the question. Here I have to say this one goes with figure 1, so you kind of have to go back and look at it. So if I try to paste it there so that you don't have to go back and forth. Yes. So 13 tops, 10 minimum. I like to have more than 10 because again, if there is one incorrect, then it brings more down the grade. So if you have more, there's more room for small mistakes, 1 question or 2 questions. Okay. All right. So that's all we want to.